Let's add a new stream. Again, by this point, you're seeing the procedure, right? I wanted to call it a habit, but there's a routine here. Add a stream, enter the material, add a calculation, done. So this calculation we're going to call precipitation point. Rename it. This is actually one of the more important types of calculations with the software, because solid liquid equilibrium is ubiquitous in all types, in many systems, not all, in many systems. And so knowing when a phase is going to separate and the composition of that phase is actually quite important. All right, now for the first time, we're actually going to change our units. We're going to leave for the mole units, and we're going to go to concentration, or really, excuse me, ppm units. So the way we're going to do that is we're going to click on the units manager. Chris would shoot me if he heard me say that. Actually, Sachin would, because he's the one who developed it. Here's my units manager, right? I clicked on that button there. Right now it's set to metric batch moles. What I mean by that is the units, again, are metric. So that's going to be grams, liters, degrees Celsius, atmospheres, joules, and plus other things that I don't remember. Alternatively, we can go CGS, right? That's going to be cubic centimeters, grams, and gosh, I don't remember anymore. Kelvin, I think it is, and maybe pascals. Okay, and then there's English. English is going to be pounds, cubic feet, pound moles, and yeah, that's pretty much Fahrenheit, and then PSIA. And then you have other things down here, which are more specific to what we call the ScaleChem software. We're not going to worry about that. For the most part, OLI, even though we're a US company, works in metric units. Okay, we're trying to drag the rest of the country along with us, but it's been a hard slog trying to get the US to go into metric. But that's okay. So much of our plants are built in with English units that we're still there, but we can accommodate them. But for now, we're going to keep the class in metric units. Batch versus flowing. Okay, originally OLI started out as kind of like a chemical engineering company. So engineering flowing processes, that's kind of like where our basis is. Okay, it's not entirely true because we actually did flash calculations first, but we recognized that the money was in engineering. So that's why we have flowing units, and we have process simulators, and also links to other process simulators. And those simulators require flowing units, kilograms per second, cubic meters per hour, cubic feet per minute, whatever it is, GPM, things like that. Okay. And then lastly, you have six types of bases to use: mass fraction, mass, mole fraction, moles, concentration, and molar concentration. In this case, we're going to use mass fraction units. That'll give us ppm. Okay. But not yet, because we actually have to tell it we want to use ppm. So now that you've changed it to metric batch mass fraction, the next thing you're going to do is click on the Customize button. Once the software says, okay, metric mass fraction, everything that essentially gets measured or entered is in fraction units. Now, when we look at this window here, actually have to spend about 4 or 5 minutes explaining this before we do the calc. The stream inflow, right? I'm actually going to show you on this grid here. The stream inflow is this right here, stream amount. Once I press OK, that moles is going to turn into kilograms. The inflows here, right? That's what we have right here, inflows. That's going to go from moles to mass percent. And then, even though we didn't spend a lot of time looking at it, when we look at our report, right, the composition of the water phase will be at mass percent, vapors mass percent, solids, et cetera, will be in mass fraction or mass percent. And then lastly, with respect to the type of units, right, you can see what we're using here. So metric is kilograms, not grams. Sorry about that. Anyway, we have one change to make right now. We'll probably make more later. We're going to change the mass fraction units here. You see where it says mass percent? We want this number here not to be mass percent, but to be ppm. So click on this cell here where it says mass fraction and change it from mass percent to ppm. Then you can see everything above here change. Now our inflows will be ppm, and our output for every phase will be in ppm as well. Conditions, the temperature and pressure will still be degrees C and atmosphere. If we had chosen flowing units, the units would have been per hour, okay, plus everything else that's here, but we're going to ignore this for now. So just make sure you've done two things. You've changed your units to metric batch mass fraction, and then when you click on customize, the second to last row where it says mass fraction, change it from mass percent to ppm mass, and then press OK. Automatically, the software says, okay, you're not really using the units that my default units, you're using more of a custom unit set. Because you're not using mass percent, you're using ppm. So we're going to label that custom. Okay, but it still has a mass fraction basis. Press OK one more. And what you're going to now see is, sure enough, the stream amount is in kilograms and the inflows are in ppm. So that's a quick 3 or 4 minute introduction to the units. There's a lot more we'd want to do with units because they're actually quite a powerful tool, and using them right actually can make your life a lot easier, because then you don't have to worry about doing back of the envelope scratch calculations to say, oh, how do I convert this to something else? Right? So, okay.
Hey, AJ, the velocity in custom here, so will be meter per hour. Is that about right? That's the what we selected.
Right. If we were to stick with these units, then yes. So we would probably, actually, there may be a different unit set. If we're looking, for example, like corrosion, right? Corrosion tends to have, for velocity, have its own unit set. So you can see there it goes meters per second.
Okay, so okay. So for the corrosion purposes, it will use meter per second, but for any other velocity, for other purposes, we'll use meter per hour.
Yeah, well, keep in mind, there's velocity and there's flow, right? There's Q, which is the flow. That's the quantity that get moved per time step. That's going to be in hours. But when you're talking about things like shear strength or shear, which is what either the velocity does or the volumetric properties with the diameter, these are really just to calculate the shear stress. So they don't actually get involved in knowing what that Q is, the material that's getting transferred. Am I clear on that? We have two.
Yeah, I understand there's a component for the shear stress, but also there's a contributing factor to corrosivity as far as removal of scale and other pertaining corrosion, erosion type component to it. So is the velocity will be meter per, if we with a custom that you said, will velocity be a meter per second or a meter per hour?
Yeah. Now you're actually brought up a point that we haven't thought about yet. We haven't integrated our corrosion model with our thermodynamic or flow model. Sounds kind of strange, but let me explain it this way. Our corrosion model is transient. In other words, you do a quick flash calculation. At that point, what's the shear stress based upon either velocity or volumetric / diameter? And then the software calculates essentially the thickness of your diffusion layer. But there's another part of this, and that is you've got that physical effect. One, you've got material moving, you've got a length of pipe. You got material moving from the start of it to the end of it, right? How the composition changes over time, right? And like you're saying, exfoliation or other type of physical removal of McKinowite or whatever it is. That part there is a flow model, and that's the part that we don't do. So as a result of that, the integration of these variables with this, let's say this time step, hasn't been made. And in fact, if it were to be made, it wouldn't be done with this software. We would need a dynamic simulator that could look at 4 dimensions, right? 3 spatial dimensions and time. And this tool right now has essentially no time dimension. It's a flash calculation. Now, but I almost want to keep on having this conversation because I love the idea of actually integrating that story, those phenomena. But that's not the tool. This isn't the tool that would do that.
Sure, it makes sense. Thank you for the clarification, AJ.
Sure. Yeah. Okay, cool. So we're going to get this calculation done, and then we're going to take a break. All right, so we've got the precipitation point stream ready. We have our inflow units ready, right? Now we're going to start adding components. The first one is going to be calcium chloride, CaCl2. And you're going to add 10,870, 10,870 parts per million of this. Okay. We're just going to assume this is a brine, essentially could be like a completion fluid, or it's a brine. Actually, you guys in Orange, Texas, right? So it could be a brine, let's say, from essentially one of the from the Gulf of Mexico, from subsurface upper Gulf of Mexico, that's going to be used to make essentially caustic electrolysis process. Magnesium chloride, MgCl2. Let's add 9325 of that. And then there's always some CO2 present in geologic fluids. So let's add 431 of that. Okay. Now, obviously, this is very dilute. So the brines I'm talking about would be much more concentrated than this. But just for grins, we're just going to say that maybe that's what we're looking at here. Okay, a very high hardness brine. And that's pretty much it. We're done adding stuff. But what we're going to do is we're going to instruct the software to tell us to add caustic to the system to raise the pH. But our interest is to find out at what pH will salt start precipitating. So we may want to raise the pH of this brine, but we have to be careful that we don't raise it too much, because then we'll start precipitating out material. And then we've got a second phase that we've got to filter out and deal with. So in this particular scenario, we're going to use the precipitation point to figure out how much caustic that I could add before I run into phase problems. Essentially, start precipitating out salts. So we're going to add a calculation. Let's call it single point. Again, that's the one we're doing right now. Isothermal, we're going to switch that to precipitation point. And the next step is actually kind of like, well, ambiguous or arcane. Like, I'm going to tell you to add calcium carbonate as the scaling. And you should be coming back and said, why would I know that? But we'll worry about that later. So for now, what I want you to do, again, once I change this to precipitation point, you see you've got what's now a calculation parameter grid again, right? Subgrid here. It's got two entries, precipitant and adjusted inflow. We're going to select calcium carbonate, CaCO3 from this list, calcite. We're specifically looking for calcite as the scale that's going to come out. And then we're going to adjust what we know we wanted to adjust, which is going to be the caustic. Okay. What you're going to notice in this case is that the caustic doesn't show up. So this is an example where we say, oh, okay, I don't have the pH adjuster that I need to. I need to add it directly. So there's no caustic shown here. You go back here to your grid. You can either add it at the top level or here. We'll add it here, sodium hydroxide. Now you can go back to your adjusted inflow. You should find caustic present and you select it.
AJ, what can we, in this particular example, instead of using NaOH, we use KOH?
Yep.
Just to see the difference.
Sure. Let's type KOH instead. Both cases, they are strong bases, so it doesn't matter. Which means they complex very little. And the only difference you might have, actually, they won't have any difference here. So we'll just run the calculation, and then we can always talk about any differences if you're kind of curious about it. All right, we're ready to press calculate. And we know we're ready because the calculation item button is green, right? If the calculation wasn't green, it usually means that because we forgot to enter something. I tried to do it that way. Okay, next time I'll have to do it for you. So press calculate. And there are two things we're interested in. One, at what pH we can get to before scale starts forming, and how much KOH needs to be added in order to get there. And both pieces of information can be found in your summary section. So again, think about it just as a black box right now. We're saying we can get to about pH of 6.1 before scale starts to form. Or we can add about 290 ppm of potassium hydroxide before that scale starts to form. Now, we selected the scale to be calcium carbonate, but that's simply because we know that's the problem in this case. So if you go to the report, what I want you to do now is actually jump right to the scaling tendencies table. And what you'll notice is that the scaling tendencies shows one row there where the values for the pre and or the post is set to 1. What that means is, especially for the post, you probably don't see the pre, so ignore this for now. So you can see one entry where the value is equal to 1. That 1 means that that solid is present in the system. That's because we forced it to be present. Okay? Everything else has values of less than 1, which means those solids are subsaturated. So ostensibly that means that as I was adding potassium hydroxide to the system, calcite was the first precipitate to form. Now, of course, we knew that before we did the calculation that calcite would form. We just didn't know at what pH it would start to form. Now we know it's going to be at about 6.15.
So AJ, one, designate in this table, scale and tendency, one, designate the threshold at which scale is thermodynamically stable. Is that okay?
Exactly what it is.
And anything else that means it did not quite get there, still has not formed anything, it did not precipitate to anything.
That's right. Anything that's less than 1 means that the system is subsaturated with respect to it. What that means in practice is that I could add more of that material, that pure component material, and it will dissolve. So for example, you can see magnesium carbonate right here. It's got a post-scaling tendency of essentially 0.0005. That means I can add a whole lot more magnesium carbonate to the water before it starts precipitating. But since there's always, the fun thing about solid liquid chemistry is that there's always what they call competing ion effect. So I may add more magnesium carbonate to the system, but that carbonate will probably react with calcium to form more calcite. So I may in fact never precipitate mag carbonate because there's too much calcium in the system. I'd have to get rid of all my calcium before magnesium carbonate starts to precipitate.
Okay, and we can play with the temperature and see what happens.
Yeah. And tomorrow, Thursday, when we start looking at surveys, we'll be able to do this thing automatically. You can look at precipitation points as a function of temperature. And it gets kind of interesting looking at solubilities of materials that way. Okay, I went a little bit long. It's 17 minutes past the hour. We're going to stop till we get to about 20. Take a break. At 25 minutes past the hour, we'll come back. That'll give us the last 30 minutes or so to finish up with this training. And then we'll spend the last 5 minutes saying what we're going to be doing on Thursday. So let's take a break, and we'll see you guys at 25 minutes past. Went to Oman, first time 20 years ago. Ever since then, I drink tea, certain kind of tea with evaporated milk or dry milk. The flavor is just amazing. I don't know if you've ever had a chance to go to that region, but I mean, it's like ambrosia, drinking that tea.
Did you see Oman or Amman?
Oh, Oman, no, Muscat. Yeah. Amman, Jordan? No, yeah. I don't know. I've never been to Jordan, so I don't know about that. But in this case, it was Oman. Okay, good. Time to get started again. One of the things we haven't done with the precipitation point is to look at the chemistry in a little bit more detail. And I don't want to spend a whole lot of time on it other than just making you guys look at the species output. Okay, and that's pretty much it. Because again, so much of the story about why things happen are either going to be in the species output table or the activity coefficients table, or even in some cases, the equilibrium constant table. Okay. So in this case, what we're curious about, and again, we're not going to dig into too much further, is what are the dominant species in this system? So as you might expect, it's going to be the free chloride ion, the free calcium, the free magnesium, the bicarbonate, and the free potassium. There's really nothing special.
Ed Jay,
yeah,
Jay, we lost you for like 10 to 15 seconds there.
Oh, bummer. Okay, yeah. Actually, my wife would say, lucky, you guys got lucky. But now that I'm back, you're going to have to listen again. So one of the things we're going to be doing here is just describing, learning about, what the chemistry was like in this calculation stream. If there's anything special about the speciation or the activity coefficients that caused the calculation to produce the properties that it did. Now, in this particular case, there's not a whole lot that's special here, but nevertheless, I just want to get you guys in the mode of when you do a calculation and you get the numbers you want, or more importantly, when you don't get the numbers you want, you look at certain tables to find out, well, why did these properties get produced? And one of the first areas you'd look at is going to be like the species output table, because you're going to want to look to see how the system essentially speciated. Keep on using that word speciated, but it's an important word in chemistry. And in this particular case, you can see that virtually everything is as the free ion, which means that the species in the water were acting like as marbles, charged marbles, but they really weren't bonding with each other. The first thing that you see bonding with each other is going to be this calcium carbonate ion pair. But the concentration is less than 1 part per million, right? Magnesium carbonate ion pair, 0.3 ppm. So for the most part, the predictions that the software is producing is simply because you've got essentially cations and anions that are behaving normally by themselves, and you just reached a pH where the carbonate, where enough carbonate formed, in this case bicarbonate, right, or free carbonate, that it reached the saturation with the calcite saturation with the calcium ion, or more specifically, the reason that solids formed in this case is simply because you reached the saturation of calcite. But everything else in solution pretty much behaved what we'd call normally. And the reason I'm saying normally is because everything is essentially as their free ion, almost like you would expect it to be if you didn't, let's say, study water chemistry. The funny stuff, sometimes it's important, are down here, like this calcium chloride complex. This is an ion pair. It's very small, but this could be very important at high temperatures and high calcium or high chloride concentrations. That may in fact change the calcite solubility. Okay, here's a magnesium hydroxide ion pair, right? Here's a calcium hydroxide ion pair, etc. So as you start using the software, you may or may not find yourselves curious or wanting to understand why these other cations, anions, or ion pairs formed. And again, you can investigate it yourself, or you can ask us about it. But ultimately, what will happen is, in some applications, these ion pairs will end up controlling things that you didn't expect them to control, like solubility. Anyway, okay, let me stop there and see if there's any questions about this precipitation point. Let me ask you a different question. How many would find themselves looking at solid-liquid reactions and wanting to do precipitation point calculations?
I am very interested in that, AJ.
You are, okay. All right, good, yeah. And we can go further with this. We'll look at again, and when we look at chapter 3, because we're going to look at solubility versus temperature and pressure. Okay, we'll probably do that with barium sulfate as an example.
So AJ, it means that like calcite is in the solid form, it precipitates, but there is still some calcite in liquid phase, right?
Well, that's a good question. Yeah, I'm glad you asked that question. That actually is not calcite. That's an ion pair. So calcite, and this is an interesting thing about how minerals and chemistry and unit cells, stuff like that exist. Calcite, calcium carbonate, is essentially a polynuclear, polyatomic structure that has a known unit cell. It's I think it's rhombohedral type cell. They're all oriented in certain locations, and it's given the name calcite. This here is essentially one calcium and one carbonate bound together. And this is the concentration of this thing bound together. So this is still surrounded by water.
AJ, we lost you for 20 seconds now.
Wow.
I'm not losing AJ actually. So
Yeah,
it's like
I'm
it
not
is
losing him either.
yeah, it's specific to maybe your computer or connectivity.
Oh. Okay.
You know, you want to come back
Yes,
in again? And,
Maybe.
you want to come
I
out
do.
and come back in?
Barely. Maybe I have a singular. So everybody else listened to AJ just fine except me.
Yes.
Yeah, I heard myself too, if that means anything.
Okay.
Do you know if you
Okay.
want to try coming back, logging out and coming back in, that might, I don't know if that'll help. I'm not a computer person. But otherwise,
Oh,
if you
I
miss
think the network is back now.
oh, okay.
I'm sorry. What did you say?
No, that's nothing. If it's working, great. We're in good shape.
Okay.
Okay, good. So that means I'm getting feedback though that spending more time on this is a good idea. Also, I got the question that I want from Faisal, and that is, what does this mean? Is this really a calcite molecule inside the water phase? And that gave me an opportunity to explain when we put the mineral name here, but that mineral name is specific to this column. If it's in water, it's not actually a mineral. It's just the ion pair, one calcium and one carbonate bound electrostatically together and then surrounded by water. And it's what I was actually, when I was talking about before, is that sometimes these ion pairs actually can be problematic because they could change the solubility of materials. But in this case, it doesn't.
With temperature, right?
With temperature and pressure, and also ion ratios. More calcium, less chloride, more chloride, less calcium. Yeah.
Okay.
Okay, we'll keep on going because I still have a couple more calculations to get done here. Actually, you know what? Rather than do these additional calculations, I think we're going to start actually doing the chapter 3 calculations. There were at least 2 more calculations that I wanted to do for you guys. I wanted to do with you guys today. That is, it was to do what's called a custom calculation and a redox calculation. What I think I'd like to do though, for now, just to make sure that we cover it, is to start with the survey calculations, chapter 3. And then we'll come back to those calculations at the end of Thursday. I can assure you that we will cover them, especially the redox ones, because they're really, really interesting. But because I'm a little bit worried that we won't get everything covered, I want to jump right into the survey calculations right now. Anyway, blah, blah, blah. I'm done.